In this section of lectures, we are going to be studying a very special theorem to complex numbers called De Moivre's theorem. And we are also going to be looking at some of its applications. So what exactly is De Moivre's theorem? Now suppose we are given a complex number z, whether we are given it in polar form or exponential form, it doesn't matter. Okay, so I'm going to go through the polar form version first. Now let's consider z cubed. Because of what we have seen from the properties of argument and modulus, I know that the modulus of z cubed will be the modulus of z cubed, which will be just r cubed. And the argument of z cubed will be 3 times the argument of z, which will be 3 theta. So this tells me that I can actually write z as r cubed times of cosine 3 theta plus I sine theta. And a similar result will hold based on similar concepts for the case in exponential form. So De Moivre's theorem is actually discussing what will happen if I have, instead of z cubed, z to the power of n. And what the theorem says is very simple. If we look at this below, then what the theorem says is just z to the power of n is r to the power of n times cosine n theta plus I sine n theta for all rational numbers n. And this is very powerful because it is not just for real numbers, but it is also extended to include fractions as well. So numbers such as z to the power of half, it will also apply. Okay, which means that we can use this essentially to find the square root of a complex number, for example, which is something that we have not been able to do up till this point in time. Okay, so if we are given z in exponential form instead, then it will look like this. But it's essentially the same thing. Okay, allow me to focus your attention. Essentially what happens is the modulus is raised to the power of n, while the argument is just multiplied by n, and that is it. So let us take a look at one very quick and simple application of De Moivre's theorem. Suppose I was asked to find the value of this expression, or to evaluate this expression. Well, by De Moivre's theorem, I will know that effectively if I were to raise a complex number z to the power of n, in polar form I will get r to the power of n cosine n theta plus I sine n theta. And in this case, let us try to identify what is r and what is theta for this question. Now let's focus our attention to what is within the bracket over here. And I can see that this is of the form r cosine pi over 5 plus I sine pi over 5, where r is equals to 2 and theta is actually just pi over 5. So very quickly, I would know that if I want to raise this whole thing to the power of 5, then what I would have will be, in this case, 2 to the power of 5 times cosine of 5 times of pi over 5 plus I times of sine 5 times of pi over 5. Which is exactly what is printed below here. And if I want to evaluate this, I can see that 2 to the power of 5 is simply 32. Cosine pi plus I sine pi. And what is cosine pi? Cosine pi, I know, is actually a value of -1, while sine pi takes on the value of 0. Okay, so therefore, the value of this whole thing is simply -32.